Hello, everyone. As usual, I am ecstatic to introduce our next speaker in CHAMP. Today we have Sara Jones from the University of Arkansas, who's going to tell us about Lyubeznik numbers of unmixed edge ideals. Sara.
All right, well, thank you very much. And yeah, first of all, I just want to thank the organizers for even giving me this opportunity to talk to you about my research today. I've been pretty excited about it, so I hope y'all enjoy it as well. So the title for today's talk is, already misspelling it, it's going to be Lyubeznik numbers of unmixed edge ideals. Okay, and just by way of setup a little bit, we'll let R throughout the talk be the polynomial ring in n variables. We'll let I be an ideal in R, and D will be the dimension. And then specifically, since I'll be zooming in on edge ideals, I'll go ahead and do a little bit of setup with some graph things. So for example, G will be a simple graph. And if you haven't heard it before, a simple graph is simply a graph with a finite number of vertices, no loops, and then there's at most one edge between any pair of vertices. And then VG will denote the set of vertices in G, and EG will denote the set of edges. And then last one, a lot of my work is going to end up using the graph complement, which we denote GC. And in particular, what this is, it just means that it has the same vertex set as the graph, but the edge set of the graph complement is the complement of the edge set of G. So if there's an edge in G, it's not an edge in the complement, and vice versa. Okay, so after the setup, with the setup being done, let's look at the definition of a Lubeznik number. So here we are given I and J. And so the Lubeznik number of R mod I with respect to I and J is going to be denoted lambda ij, and it's going to be defined to be the dimension of these X modules. Where this is referring to the local cohomology of R mod I, make that I a little bit more legible. And we'll simply define that for the purpose of today to be the direct limit of these X modules. But we won't be having to do too much with that definition. So we'll just simply kind of define the local cohomology is that, and then we'll actually see later that we're going to actually be using a different way of calculating the Lubeznik numbers as well, instead of having to go through these X modules. Before I go into some examples though, to see how we can do that, let's look at a few properties that are going to be useful. So the first one is that lambda dd, and remember that d is the dimension. So we actually refer to this one as the highest Lubeznik number, and there's a property that says this is never zero. So that's our first property, always non-trivial. Second property we'll use today is that highest Lubeznik number is 1 if R mod I is cohomology, or even just S2 would work as well. So there's one property we have there, and then in particular, we see a little bit more after we look at this property. We see that lambda ij is equal to 0 if j is less than d or I is greater than j. And what this actually allows us to do is represent the Lubeznik numbers in a d+1 by d+1 matrix. which we denote big lambda of R mod I, and where the Lubeznik numbers are lined up as such. We have lambda 0, 0 here at the top. We'll have our highest Lubeznik number down here in the bottom diagonal, and then we'll fill in the rest from there. There's 0, 1, and we'll go up to 0D. We'll fill in one more along the diagonal, and then it goes down. And actually, by this property up here, we actually see we have zeros everywhere below the diagonal. This is a property of Lubeznik tables.
Sara, sorry, can I ask a question? Do you maybe mean J bigger than D?
It should be.
So it's the ones that are 0, right? So that there's finitely many.
Well, it is also for J bigger than D. Because that's what gives us even that it can be condensed into a D+1 by D+1 matrix. But it also should be J less than D, which is what gives us the 0 below the diagonal.
I see. Thank you.
If I understood that correctly and thought that through correctly in my head real quick.
Thanks.
Okay, so then the fourth property that I mentioned, we can even say more specifically based off of property 2, which was that the highest Lubeznik number is 1 if R mod I is cohomology. Now that we see this Lubeznik table representation, another property says that the Lubeznik table of R mod I is trivial. And by trivial, we mean it's actually 0 everywhere except for the highest Lubeznik number, which in this case is 1. When you have a trivial Lubeznik table, we've already seen that that can never be 0. So that one is 1. And that's trivial in the case that I is a Cohen-Macaulay square-free monomial ideal. So we already see a pretty wide class of rings here that gives us a trivial Lubeznik table. And in fact, there's been a lot of people who've even done a lot of research just on classes that give us trivial Lubeznik tables. So that's already one area of research or one direction of research you can go with Lubeznik tables. So let's look at another property. We have 2 more that I'll list today. One is the Euler characteristic, which does what you would probably expect the Euler characteristic property to do. It looks at the alternating sums of the Lubeznik numbers and actually tells us the alternating sum of those is always going to be 1. Okay, so that's one property. We'll see that actually in the next example. We'll see that property observed there. And then the last one we'll mention today is the depth property. And it tells us that the 3 upper diagonal entries in all the columns up to the depth are actually going to be 0. You can gather information about the depth by looking at the Lubeznik table as well. Okay, and again, we'll see that carried out with the next example. So just some useful properties there to kind of get us in the habit of, or get us used to, I guess, looking at Lubeznik numbers and how we can start calculating them practically. So let's look at this example. We'll let R be a polynomial ring in 4 variables. And I will be the ideal generated by XZ, XW, YZ, and YW, which is actually the union of 2 planes. Okay, so in this example, note here first that D is equal to 2, the dimension is 2. And so already we know the size of our Lubeznik table. It's going to be a 3 by 3 matrix. And we already know we have zeros below the diagonal. So that leaves us with just 6 Lubeznik numbers to figure out here to get this table. So we'll use some of our properties to do that. First, our depth property tells us that, so since the depth here is 1, it doesn't give us a lot of Lubeznik numbers, but it does at least tell us that the lowest Lubeznik number is 0. So that gives us one of the Lubeznik numbers we need to fill out this table. And then I won't go through the details of using the local cohomology techniques, but you can use some standard local cohomology techniques to calculate the other two non-trivial ones, which is the highest Lubeznik number, which ends up being 2, and the 0, 1 Lubeznik number, which ends up being 1. And then again, using local cohomology techniques, you can get 0 for all the others. And so we see this Lubeznik table is given by this matrix. Okay, and we'll work out a few more of the details of how you can explicitly calculate each of those numbers instead of just some hand waving here with another technique in a minute. But just to kind of give you an example, this is one Lubeznik table that we have. And if you know anything about the punctured spectrum, notice that the highest Lubeznik number is actually equal to the number of connected components in the punctured spectrum. And then this number right here, the 0, 1 Lubeznik number, is 1 less than the number of connected components in the punctured spectrum. And that's not a coincidence. We have this theorem by Walther in 2016, and he said, let I be radical of pure dimension 2, and let A equal the number of connected components of the punctured spectrum of R mod I. Then we see what we just observed in the previous example generalized. We see the Lubeznik table is given by zeros everywhere except for these two remaining entries, where this one is the number of connected components and this one is 1 less than that. So a generalization of the example that we just noticed here. And I will say that even though you can use standard local cohomology techniques to calculate the Lubeznik numbers, in general, they can be lengthy and even difficult to compute, which is what makes the next result by Montaner and Vahidi especially important, especially for me, who works with edge ideals, because they give an easier way of calculating these Lubeznik numbers for square-free monomial ideals. And since I'm working with edge ideals, this is very useful to me. So as I mentioned, it's for square-free monomial ideals. And it says that our Lubeznik number is then given by the dimension of the homology of the linear strands, and I'll say a little bit more about these terms in a second. So the Lubeznik numbers is given by this formula here, this dimension, where my pen's not working. Okay, started working. Let me make that a little neater now. Where bold K denotes the fraction field. I dual is the Alexander dual of I. And as I mentioned, this is going to denote the linear strand. Of the Alexander dual. Okay, so actually, as I mentioned earlier, we're not going to work much with the definition of Lubeznik numbers using the local cohomology. We're actually going to treat this as the definition for the remainder of the talk. This is what I work with when I'm doing my calculations and proofs. So this is what we'll kind of zoom in on for the rest of the talk. I will mention, though, that before we say too much more about the Lubeznik numbers and how you can use this to calculate them, there's some things here that we really haven't defined. We haven't defined linear strand, and we haven't defined Alexander dual. We need to know what those are before we can use this formula. So let's say a little bit about that, and then we'll actually jump into some Lubeznik numbers. So we'll look at linear strands first. So if you have this sequence, this exact sequence, And it is the minimal graded free resolution of I, where each of these terms is given by this direct sum. And the beta ij's are the graded Betty numbers of I, the ranks of the free modules. And so if you're given R, the R linear strand of the free resolution is, give myself plenty of room to write it. It's given by this sequence. Okay, where each of these terms are the corresponding terms of the free resolution. And the maps here are the corresponding components of the maps of the free resolution. Okay, so that's what a linear strand is. It's basically just a way of breaking up your free resolution so that each strand, of course, is linear, as the name suggests. So this is going to allow us to make our calculations significantly easier. And then the Alexander dual is the other piece we need. I'm actually going to define edge ideals formally first, though, because we're going to base our definition for the purpose of today's talk for Alexander dual based on an edge ideal. So first, let me define an edge ideal associated to G. So we denote it IG, and it is simply the ideal with generators XI and XJ, where XI, XJ are edges in the graph. So all the generators of the ideal represent edges in the graph. Easy example here, if G is this square with vertices X, W, Y, and Z, then the edge ideal associated to G is given by XW, WY, YZ, and ZX, and those are the four edges you have in your graph. So that's an edge ideal. And then with that in mind, we're going to define the Alexander dual of I. We'll denote it as such, and it's going to be the ideal generated by the product of variables in PM, where, sorry, I had to break this up on that line. Those are the associated primes of the ideal I. And this will make a little bit more sense when we look at an example, but yes, it's simply the product of the variables in each associated prime. Those are the generators of I dual. Not the formal definition of Alexander dual, but that's the way we're going to define it for the sake of the talk today. So an example, we'll actually look at the same graph we just looked at, the square with X, W, Y, and Z. We said that I here is going to be XW, WY, YZ, and ZX. And this is also the same one we mentioned at the beginning of the talk, that is the union of two planes. Okay, so we can write it, break it up as seeing our associated primes are X, Y, and ZW by the definition that we're using of Alexander dual. Notice that tells us if you look at the product of each of those associated primes, your dual is going to be generated by XY and ZW. So now we have what I dual is in this case. So let's continue this example out, and we'll find the linear strands of this. To find the linear strands, we need to start off with finding the minimal graded free resolution, which is going to be given by this sequence. Okay, so we have the free resolution, and then notice our Betty numbers, the ranks of the free modules are 1 and 2. And so this tells us that in particular, we have a 3 linear strand and a 2 linear strand. So the 2 linear strand is going to be given by this sequence, since this Betty number is 2, and the 3 linear strand is given by this sequence, since this Betty number here is 1. So we have our linear strands. And then looking ahead at the fact that we're using the result by Montaigne and Vahidi, we need to tensor these by K to get that we have these sequences. The 2 linear strand tensor K, of course, will just be this sequence. And similar with the 3 linear strand. Okay, again, continuing this out, we use that formula we saw earlier, and we see that the 0, 1 Lubeznik number is going to be the dimension of the first homology of the 3rd linear strand of the Alexander dual. And so it ends up just being the dimension of K, which is 1. Similar, our highest Lubeznik number is the dimension of the 0 homology of the 2 linear strand of the Alexander dual. Which ends up just being 2. And those are the same non-trivial Lubeznik numbers we observed earlier. Doing the same technique, all the rest of them work out to be 0, so I won't write all those down, but it's literally just finding your homology of each of these linear strands, and it's not hard to see based on these sequences that the rest of the homology there is going to be 0. So we do get that our Lubeznik number is the same one, of course, that we observed earlier, but calculated now using a different technique. So yeah, that's our Lubeznik table for that one. One thing I want to note here, we made the connection to the punctured spectrum earlier, but since I'm working with edge ideals, I want to start relating things to the graph. So let's see how this relates to the graph. In particular, we'll look at the graph complement. I'll remind us what the graph was. It was just a square where the vertices were X, W, Y, and Z. And so the graph complement, you switch your edge set. And so now we have X, W, Y, and Z. And if we untwist those, we see we have edge X, Y and edge W, Z. And notice here that the highest Lubeznik number is equal to the number of edges in the graph complement, which is of course also equal to the number of connected components in the graph complement. And the 0, 1 is the number of connected components in the graph complement minus 1. We're going to see in my main result that this is actually not a coincidence, that you can start making this connectedness information tie in with the Lubeznik numbers. And again, that's what my main result is going to be focused on looking at. So to do that, I'm actually going to switch to a slide portion of the talk. And my hope was that this was going to be a pretty effortless switch here. So let me switch to this. Can y'all see those slides okay? Okay. Yes, Lubeznik numbers of edge ideals, unmixed edge ideals. This will be the slide portion, make it a little bit easier to show some of these tables without writing them all out. So in particular, here's the main result. We'll start off with letting I be an unmixed edge ideal of dimension D in the polynomial ring in variables, where G is a coportal graph, and I'll say a little bit more about that coportal graph in a minute. Then the Lubeznik table of R mod I is given by this matrix, where J is given by the number of connected components in the D minus 1 click graph of GC, and those upper diagonal entries are given by the difference in the number of connected components in these 2 consecutive click graphs. Notice here first that we are using pi naught to represent number or the set of connected components. We'll use that as the convention throughout the rest of the talk. And also notice so far we don't know what coportal is. And we don't know what these click graphs are. So before we can understand this theorem, we obviously need to explain those a little bit. So I'll kind of give us a little bit of background on some graph things, some graph terms. The first one that's beneficial to know is a complete graph. Pretty easy definition here. It's just a graph with an edge connecting every pair of vertices. So every possible edge is there in the graph. Some examples. The first graph is a complete graph on 2 vertices. The second one is a complete graph on 3, and so on and so forth. It recognizes every possible edge. Okay, and then the next one is a clique of size m. A clique is simply a complete subgraph. So it's a subgraph on m vertices, but that subgraph is complete. And then a maximal clique would be a clique that's not properly contained in another clique. So we'll look at this example to make sure we're comfortable with this definition. Notice first that in this graph, all the vertices are already cliques of size 1. All the edges are cliques of size 2. There's 5 triangles in this graph. Those are all cliques of size 3. And then we only have 1 clique of size 4. That's given by that square in the bottom right. And then the maximal cliques are given by first this triangle. It's a maximal clique of size 3. This square in the bottom is a clique of size, maximal clique of size 4. And then these 3 edges. Those are all the cliques that's not contained, properly contained in another clique. So those are our maximal cliques. Okay. One more example, notice in this example that all the maximal cliques are the same size. The only maximal cliques we have in this graph are triangles, cliques of size 3. So all the cliques are the same size, and we call this a pure graph. A pure graph is a graph where all the maximal cliques are the same size. So G2 is definitely a pure graph, G1 is not a pure graph. Next definition is a cycle. A cycle is a path that begins and ends at the same point. And before we look at an example, we'll define this one as well. A graph is chordal if every cycle of length at least 3 has a chord. And a chord is simply an edge connecting 2 non-adjacent vertices. And then cochordal simply means that the complement of the graph is chordal. So looking at this example, there are several cycles in here. The triangle at the top is a cycle. If you continue that down with a square at the bottom, you have a cycle of size 5. There's several cycles here. It's just again a path that begins and ends at the same point. But do notice that if you look at the square in the bottom left-hand side of the graph, you see that you have a cycle of size 4 there given by that square, but there's no chord in it. There's no edge connecting any of the pairs of non-adjacent vertices that you have. So this would not be an example of a chordal graph because it has a cycle of length 3 or greater, so in this case 4, that doesn't have a chord. Okay, so this is not a chordal graph, whereas this one is. It also has a cycle of length 4 given by that square, and then also a cycle of length 5. But notice any cycle of length greater than 3 there has a chord. And so this one definitely is an example of a chordal graph. And to give you all a second to process some of these graph terms, I'll mention that we're going to actually see later that we needed this cochordal condition. And again, remember, cochordal is simply that the complement of the graph is chordal. We need this cochordal condition to limit the projected dimension of the Alexander dual, which is what we need to calculate the Lubeznik numbers using the result by Montaigne and Vahidi. And so we're going to look at the homology of these linear strands of the Alexander dual. And so again, this is the condition that's going to be needed. It's too much to work with the free resolution of the dual of every edge ideal, since they can be arbitrarily large. So we needed to limit the length of the free resolution. That way it made it more manageable to work with. And we found that cochordality was actually the perfect tool for the job. So very important conditions we have here, which we'll see later. So this takes care of saying what cochordal is. So I guess the next step is to say what the clique graphs are. In short, these are going to be the ways that I get from the linear strand to the graph. That's my whole goal, is to be able to describe the Lubeznik table of the edge ideal using purely combinatorial information found in the graph. And this is going to help me make that link. Before we introduce those, let's get where the link actually came from between the graph and the linear strand. So that is using the Egan-Rayner formula that we see here. So yeah, it's by Egan-Rayner. It was in '98, and he says that the graded Betti numbers that we see here are given I'll go ahead and mention, notice there that this is the graded Betty numbers of the Stanley-Reisner ideal, and it's given by this sum over all the faces in the dual of the simplicial complex. And then it's looking at the sum of the dimension of the reduced homologies of the length. But I will say that we won't say much about the Stanley-Reisner ideal, at least for the sake of this talk, because we have a result of Ferrarello in 06, which actually says that an edge ideal is a Stanley-Reisner ideal of the clique complex of the graph complement, and I'll mention a little bit more about that in a second. But because of this result, we can actually instead say that the graded Betty numbers of the Alexander dual are given by the sum over the faces in the clique complex of the graph complement of the sum over the dimensions of the homology of the lengths. And notice there at the bottom, it says that the clique complex of the graph complement is simply the simplicial complex whose faces represent cliques in the graph complement. And so facets in the clique complex would be maximal cliques in the graph complement. So it's not hard to make that interchange between the simplicial complex there and the graph complement. And so this is going to be that link we need to get from the graph to the linear strands explicitly through the Betty numbers here. Okay, but do notice that we have this link here that we don't know anything about yet. So we'll define the link, and I think that will be the final piece that we need to get back to the main result. So the link, here's the formal definition of it. It's a little bit easier to see through an example. So if you look at this graph and you look at the vertex F and we want to find the length of F, it's basically everything you can join with F to get a maximal clique. So notice there's two maximal cliques containing F, the one in blue and the one in red. ABF is a maximal clique containing F, and so is DEF. And so again, the link is everything that you can join with F and still get a maximal clique or a face if you look at it as far as the simplicial complex is concerned. And so you see that the link is actually given by AB and DE. You can join AB, you can union AB with F and get a maximal clique, and the same with DE. So this is what the link is. Okay. So I'll mention here that, so we have this link now between graphs and linear strands, explicitly Betty numbers, but by the Egan-Rayner formula that we just observed, notice that really the only graph information we need is going to be the link. So I introduced a family of graphs, which I call the clique graphs, that simplifies the graph that we're working with, but it keeps the information that's relevant to the Betty numbers and ends up to Lubeznik numbers. So let's go ahead and look at these clique graphs. Here's the definition. A clique graph, first off, you need to be working with a pure graph to begin with. Let G be a pure graph. Remember, that's where all maximal cliques have the same size. And so the clique graph, in particular, the I-clique graph, is the graph where the vertices of the clique graph are representing maximal cliques in G. So there's a vertex for every maximal clique in G, and there's an edge between a pair of vertices if the intersection of the maximal cliques they represent has a size greater than or equal to I. The intersection is size greater than or equal to I. So that's what a clique graph is. Again, we'll look at an example of this to kind of get a better understanding of it. Say this is our graph, graph G. We have four maximal cliques, A, B, C, and D. And so we already see that the clique graphs are going to have four vertices. We mentioned that there's going to be a vertex for every maximal clique in your graph. So we have four vertices. And then for the, notice here, this is the clique greater than or equal to 3 clique graph. So it has an edge every time that the pair of vertices in the representing maximal cliques in your graph, if that intersection has size greater than or equal to 3. Notice that none of our pairs of vertices intersect at a triangle, and so there's no edges in that clique graph. Whereas in the 2 clique graph, the edges are representing intersections of size 2, and notice A and B in your graph G, those maximal cliques intersect at an edge, which is a clique of size 2, and the same for B and D, so they get an edge between them. The 1 clique graph, they get an edge if the intersection in G is size at least 1. So you definitely keep B and A and C and D since the size of that intersection was 2. But you also pick up the edge BD and the edge BC in the clique graph, since maximal cliques B and C intersect at a point, and so do B and D. zero click graph, A and C intersect at a click of size 0 since they're disjoint, and so do A and D. And in fact, you can easily see here that any zero click graph is going to be the complete graph because all maximal clicks are size at least 0. Okay. So this should be the final piece that we need for our main theorem now. This tells us what cochordality is, and hopefully we have a little bit of understanding of what the click graphs are. So we'll return to the main theorem. So just to remind you, it said if I is an unmixed edge ideal, and I'll give you a little sneak preview here, the unmixed edge ideal is what forces us to be working with a pure graph. So that's what's going to allow us to use the click graphs. And then again, working in a polynomial ring of size or within variables, and where G is a cochordal graph. And then the Lubeznik table, again, it's given by this matrix. And now hopefully we know a little bit better about what that J and the CI are all talking about. All talking about connectedness information in our click graph. Okay, so let's look at an example. We'll return to this example. We just found all the click graphs for. So consider the edge ideal when the graph complement is given by this graph. So we have maximal clicks A, B, C, and D. And again, that's going to give us points A, B, C, D in our click graphs. So we see that the 3 click graph has 4 connected components, and that the 2 click graph has 2 connected components, and then 1 connected component in each of the 1 and 0 click graphs. We see that modeled in that table as well. So what my main result is saying is that we can actually calculate the Lubeznik numbers, the whole Lubeznik table, based on purely the information found in this table right here, the number of connected components in the click graph. We don't have to go through the link. We don't have to look at the Betty numbers, the free resolution, any of that. We can simply look at the number of connected components in this click graph. So by the theorem, we know the Lubeznik table of R mod I is given by this matrix where we have non-trivial numbers C0, C1, and J, where J, according to the theorem, is the number of connected components in the 2 click graph, which we just saw in the table was 2. And then C0 is the number of connected components in the 1 click graph minus the number of connected components in the 0 click graph. Both of those were 1 that we saw in the table. That gives us 0. And then the 1 click graph is the number of connected components in the 2 click graph minus the number of connected components in the 1 click graph. And again, as we saw in the table, those were 2 and 1 respectively. And so we get 1 as that entry. And so we see that this is going to give us our Lubeznik table. Again, without having to find Betty numbers, without having to find the link, linear strands, any of that, local cohomology, simply looking at the number of connected components in these click graphs. Okay. All right, so we still have plenty of time here to look at a brief outline of the proof. We won't go into a lot of detail here, but just to kind of get a little bit of an understanding of how this proof goes. The first step is basically finding the linear strands. We know we need linear strands to be able to find the homology to calculate the Lubeznik number. So let's find the linear strands. We're going to use this fact to do so. This is the one I mentioned briefly as I was reading the theorem. We know that I is an unmixed edge ideal. That implies that the graph complement is pure. So we need that information. First to be able to use the click graphs, but it's also going to help us simplify the linear strands. And then also looking at our consequence of the Egan-Rayner formula, we see that the 0 n minus d Betty number of the Alexander dual is given by first the number of maximal clicks in your graph complement, but that also represents the number of vertices in your click graph. And I put the D click graph, but notice all click graphs have the same number of vertices, so that could be any click graph. It's the number of vertices in the click graphs. And then also a consequence of the Egan-Rayner formula tells us that the 0 n minus r Betty number is going to be 0 for all r not equal to d. And again, this is going to help us simplify our linear strands. Something else we need here is that if I is an edge ideal, then the projected dimension of the Alexander dual is 1 if and only if G is cochordal. And this is why earlier I said this cochordal condition is so important, because this is what allows us to restrict that linear strand so that we can find a little bit more homological information about it. As I mentioned, it's too much to work with just the whole free resolution of any given edge ideal. So we found a way to restrict it that still includes a wide class of examples. So putting these things together, we do see that we have these linear strands. Notice that the 0 in the n minus I linear strand comes from the fact that right above the theorem statement that says the 0 n minus r Betty number is 0 for all r not equal to d. And then notice here that the n minus I linear strand only has one term. And again, this is what is going to make this homology easy to calculate here. And we already see that with the n minus I linear strand. The n minus d linear strand is going to take a little bit more work to calculate the homology, but not much more, because in the free resolution, we see that that map phi is going to be injective. And so that map is going to be injective here as well. So we're going to use all these facts to calculate our Lubeznik numbers based on these given linear strands. So step 2 is calculating the CI from the linear strands. So to calculate the CI, all those upper diagonal entries, we're going to need the n minus I linear strand. So we'll zoom in on that. As I mentioned, the homology of this is easy to calculate, and that's all we need to calculate the Lubeznik numbers. So if you look at the homology, you get 0 everywhere except for your first Betty number, and then that's actually going to represent that upper diagonal entry in the Lubeznik table. So already we have a big chunk of our Lubeznik table. We need to find a way of relating the first Betty numbers to the click graphs, and we need to get those last 2 entries down in the bottom corner. But other than that, we already have a good start on our Lubeznik table. So let's see if we can get from the Betty number to the click graph using connectedness information. And this is how we can do that. This is where a big bulk of my theorem lies, is in proving this theorem right here, which calculates the first Betty number for us, given the number of connected components in these 2 consecutive click graphs. Okay, so notice here it says first we do have to have a cohomology graph. We already mentioned that. It doesn't need to be an unmixed edge ideal to be able to work with the click graphs. And then again, it tells us that this first Betty number is the difference in the number of connected components of these 2 consecutive click graphs. The proof of this, like I said, is where the bulk of the work lies. This is where most of the heavy lifting is. I will say it doesn't use necessarily a lot of hard math, but it's very technical, and so we're not going to go through that for today's talk. But again, this is proved to be the very important link that we need to get from the click graphs to the linear strands. After this, it's smooth sailing. So notice that this already gives us our CI entries in the Lubeznik table. We just saw in the previous slide that all those upper diagonals are given by the first Betty number, and this now shows that the Betty number is given by the connected components in the click graph. So all the CIs are now calculated. All we need now are those bottom 2 entries. So we'll look at that. That's step 3. We need the n minus d linear strand to do that. And again, we can use this linear strand, calculate the homology of it, and thanks to Montaigne and Vahidi, that will give us the Lubeznik number. So again, notice that that phi is injective, and that's what makes this homology easy to calculate. That tells us that the d minus 1 d Lubeznik number is going to be 0. And the highest Lubeznik number is given as the difference of those 2 Betty numbers. We still need to get to the click graphs, but thankfully we already said that this 0 n minus d Betty number is given by the number of vertices in the click graph. And we just have this theorem now that says the first Betty number is the difference in these numbers of connected components of click graphs. And putting them together, things are going to cancel out nicely, noticing that the D click graph, if you look at the 0 n minus d Betty number, it's given by the number of vertices in the D click graph. Well, the D click graph is where you're looking at intersections of size D, but since the dimension is D, there can be no intersections of size D there. And so you actually get that that click graph is just isolated points. And so the number of vertices is actually equal to the number of connected components. And that's how you get that nice cancellation to give you that the highest Lubeznik number is actually just the number of connected components in the D minus 1 click graph. And that's the last piece of the puzzle, last piece of the Lubeznik table there that gives us our main result. So that's all I'll do for today. Now, I guess if y'all have any questions, I'd be happy to try to answer them.
Let's thank Sarah for the nice talk. And we'll take any questions.
So if I hand you so let's say I give you a square monomial ideal generated in degree 2, so we know it's the edge ideal of something. Is it possible to know if it's co-chordal or not without actually writing down the corresponding graph? Or if I do write the graph, is there an easy way to ask if it's co-chordal or not without actually, without actually going and carefully looking at everything?
So one way is the projected dimension, but that does, of course, force you to look at the projected dimension. If that's less than or equal to 1, then you know it has to be a quarter. At least the Alexander dual, if the projected dimension of that is less than or equal to 1, then the graph complement has to be quartal. As far as just looking at the edge ideal and knowing automatically if it is co-quartal, I don't have an answer for that. Knowing that I work mostly with the Stanley Reisner ideal, and so I end up working with the Alexander dual. That's where I end up focusing more on, is actually the Alexander dual instead of the edge ideal itself, and I end up working with the graph complement much more than working with the actual graph. In fact, most of the time I don't even write down what the graph is because I know I'm just going to need the graph complement. So I don't have an answer for you right now as far as that goes, but I can look into that and try to get back with you.
Thank you. Thank you.
Other questions?
So hopefully I didn't miss this, but your result is characteristic free, is that right? So there's no conditions on the field, right? It's just, it can be whatever characteristic.
Yeah.
That's cool. That's cool. Thank you.
Nice point.
Yeah, unless there's something I'm not thinking about right now.
Cool.
But, oh yeah, no, it's just for any generic polynomial ring over a field.
Nice.
I have a question.
Okay.
So you mentioned a result of Uli in dimension 2.
Mm-hmm.
Right. So do you know if you can deduce his result from yours?
That's one of the things that I'm researching. There's actually, I don't know if you've watched my elevator pitch or not, but there's actually a lot of different connections that the Lubeznik table, Lubeznik numbers have with connectedness information. You see that there's results that say the Lubeznik table can give connectedness information found in the Hofstadter-Hünicke graph, in the punctured spectrum. There's connectedness all over the place. Now I'm showing it shows connectedness in the graph complement. So I'm assuming there's some way of making a link between all these. That's something I'm researching, but I don't know right offhand if one just immediately follows. It shouldn't immediately follow. There would be some working out the getting from one to the other. But I don't know yet whether that's just if it follows directly from one or the other, if that makes sense. I expect that they are all very much related, but I don't have anything yet to show when one is clearly evident based on the other.
Okay, thank you.
Other questions? All right, let's thank Sarah again.